Hi, hello, everyone. So I think it's the time to start this session. So we have our first speaker is Mihuku Nodri, and she will talk about recent progress on jet structure for Bienstan model. So Mihuku, you can start.
Thank you. So it's nice to be here again. So I'm Mihoko Nojiri, and I'm talking about the jet substructure for BSM study, and and as everybody probably it is very well known now that jet physics is very important for BSM, especially uh, for boosted Higgs and boosted top studies. They will be produced from heavy resonance decays, or maybe the standard model effective theory for the signature is the enhancement of the high PT Higgs boson and W and Z. So we want to have a very good sensitivity for those things. And so boosted object looks like a jet, narrow jet, and so the structure inside the jet is very important. So that also means we would need to understand the systematic. We need to understand systematically what the quark jet and gluon jet as a background should look like. So, so I'm talking about the jet itself. So jet is originally defined as from the highest PT object in the cluster, that is in 80s. But now the people start to find a more stable algorithm, and the first thing invented is the KT algorithm in 91, and then it becomes a general seedless jet algorithm. The most important development in this field is the first jet, that is 2006, so only 15 years ago. And the idea is that you want to match the pairs with the smallest distance one by one, and update the jet constituent until you reach the certain jet diameter R. And this distance is defined by the angle between the particles, and and sometimes you have a factor of the kts of the constituent particles. So depending on this factor p, can you see my cursor? And depending on the value of p, then we have a KT, Cambridge Aachen, and the anti-KT algorithm. So the jet substructure, the idea of jet substructure is started from this clustering algorithm. So this clustering algorithm merging the pairs. So if you go back to this merging algorithm, then you get a subjet. And if the particle comes from the heavy object decay, then this subject more likely satisfies the criteria, which now called soft drop. So if the the PT of the two objects is very high, then you can say that this might be coming from the hard particles. So then people come up with very nice seedless IRC safe variables. The one thing is the n subjetness, that is something minimizing the distance from the n axis. So you assume that several axes exist in the jet and try to minimize the distance to this virtual axis. Then you can get this tau that tells you that how many clusters you have in the jet. The other idea is the energy flow polynomials. This is something defined here. It's very complicated, but for very simple one here, you can see that this is just the energy correlation, endpoint energy correlation inside the jet. This is very general variables. And the nice thing about those quantity is that they are IRC safe. So in principle, you can calculate it in QCD. So then you want to build the classifier. So in this picture in the left, this is a picture, typical single event coming from top. And the center one is the average image of the top jet. And the most right one is the QCD average image. And the workflow is that you have a jet, and you might use the high-level variables like tau or energy from polynomial, or you can use the jet constituents itself to build up the classifier. And the classifier can be cut-based or BTT, or nowadays you can use the deep learning to build those things. So I will talk about deep learning because it is relatively new. So the deep learning is something like this. You have input, and then you have the function like this corresponding to each node. Here, the Wij and Bj is just a number assigned initially, and this phi is the activation function. So if it is 0 for certain small value and increase linearly with this output becomes large, and you have this multi-layer path electrons to get the output in the most right hand side. So in the beginning it is a completely random number, but you can tell that if the event is a signature, you can tell it is 1, and if it is a QCD event, you can tell that this is the other side of the number is 1. And then you have an optimization process. You define certain functions, and you might minimize this function by using a gradient flow, so that this y hat is 1 if very close to 1 if it is a signal, and y hat is very close to 0 if it is a QTD-like event. So this system is nice because it is known to have a very high representative power if nodes and layers are large, and the optimization process works well. And here, this is a list, certain summary paper already 2 years ago, and then you can find that there is many top tires created by using a neural network system with various inputs. And here, the right-hand side, the x-axis is the signal efficiency, and the right-hand side is the background rejection factor. So if you go to the higher, then you have a very nice power to reject the background. Now the one warning is that you have to be really careful about checking the conditions these plots are made. So this is in some sense, well, this is reasonably good. This is the answer after using a detector simulation and have a certain PT range, and but this doesn't have a PT marginalization. So machine learning actually using the PT information, and it also doesn't have a jet mask cut. So this number 10 to minus 3 looks really good, but you have to bear in mind that this is the condition it is made. Now, so this is one of the machine learning architecture called CNN. So this is when you have an image, then you have some filter going through the jet image, and then you have some cutoff called pooling, and so by having a multiple layer of this system, you find the correlation between the activities. So the performance of this kind of architecture, very general image-based architecture, sometimes have very nice classification performance compared to the BDT-based human-made using a human-made variables. So the question is why neural net is better than the others, and what kind of event is excluded additionally. That's kind of questions. So recently there is also some idea called particle cloud. So this actually takes the pair of the particles, all particles in the jet, and you calculate the numbers calculated from the pair of the particle called H, and you update the vertex, that is the particle, the quantity associated to the particle, and you repeat this process to get the final, before you get the final output. And this is something called the particle cloud, and this looks nice because you can directly treat the particles. So here is the example. Then this best line is a particle net, and this green one is something called ResNext, and that is basically the CNN. And so these guys have is actually the groups that gives you the best performance in this summary paper. And then what is the role on the other networks in this review paper? So there is a certain reason try to use the low performance networks. This is the IRC safety issues. IRC, so there is two objects in the jet. One is an IRC safe object that is stable against the emissions of or collinear emissions, and those they have a good theoretical prediction and nice to use. And on the other hand, there is a certain IRC sensitive object. For example, the number of tracks, the number of particles, and very soft emissions. They're more difficult to model, and we especially find that the problem having a consistency between the Monte Carlo and the simulations. So there is a certain networks which try to use only a IRC safe setup. So for example, this is a typical example of IRC safe setup. This phi is a function which only depends on the angular to the jet center, and this Zi is a fraction of energy. So this kind of 1-point correlation, if we restrict the output to this kind of energy, linear in energy, then you can get the IRC safe relation. Then there is the other one called the particle flow network, which doesn't respect this kind of structure. So you can directly compare that how these two are different. So here you can see that these lines here, this is something called energy flow polynomial. So which energy flow polynomial input. So this only use the high IRC safe handmade input. And this is a linearized version of energy flow network. So this is the IRC safe simple network. And here you can see that the network based on the n subjettiness, which use the n subjettiness up to 8. So 8 subjet correlation is used in this particular one. And these are, well, that looks a little bit worse compared to the best one, but still built on the formerly IRC safe quantity, so that might be better than the others. Well, on the other hand, here we can see that the current situation about the Monte Carlo prediction and the real experimental measurement. So here, the left one, whatever the parameter they are measuring, the left one is IRC safe one, and the right one is IRC unsafe one. And here you can see that they do not agree anyway. Within 1%, 20%, 10%, you always observe some mismatch. And but maybe you can say that this IRC safe one is consistent in this particular range, while the difference is larger here. And there is something called Lund-jet plane recently. This is the kind of visualization of jet space. So you have a jet, and you can go back to the jet clustering sequence and measuring the d and the relative angle r. And then you can use this jet clustering sequence projected into this plane of R and Z, and you can then you can regard that this region is a hard and reliable parameter region. And on the other hand, if you go this way, you will have more problems, but the soft collinear region you can probably handle, and the hard collinear region also we know how to do it. So you can actually check if your measurement and the theoretical prediction is consistent to each other. And you can see some kind of expected result that the non-perturbative region, the all simulators have certain problems right now. And maybe you can restrict yourself to the stable region of the clustering sequence. So recently there is a proposal called LUNTNet that is directly using the parameters on the Lund-jet plane to build the classifier, and they find the large improvement from particle net with limited resilience to the QCD and the detector effect. So this means, the physics is same. In hard region and collinear region, you have a better description of the theory. But if you go to the soft regions, you will have more and more problems. So this is a rough idea of what we see, that you have a higher level theory you can enjoy, but at the end you need to understand the part of the QCD, the summation, and at the end the hadronization. And we have a situation that better theory gives us a better description, but we still have a problem, the non-perturbative regime of the jet structures. So at the end, I want to mention a little bit on what I'm working with my collaborators. That is exactly talking about the soft structure of the jet. So we have so many particles in the jet, and I want to quantify these things. So to do this, I have introduced the persistent analysis of the jet. So here you can see that if there is a point, then you can introduce the circle with varying radiations. And if there is a multiple point, then we can measure, we can see that the overlapping circles in the jet. And I introduced something called Minkowski functions, which is essentially the area and the length and the Euler character of this image of the right hand as the function of R. And I use this to quantify the soft particle inside the jet. So when we have a jet, the area and length and the Euler character of the jet image with varying duration, the size of the durations, and I can discretize this information into some digitalized number, print numbers, and we can create the network using those information. And this is nice because let me stop this. This is nice because all particles are treated equally, and the geometry information is encoded, and it has a reduced statistical fluctuation, which is nice in the machine learning. And the Minkowski functional, this has a computational representation, so it saves the time, CNN minimization cost. So, and here is the result. So with I take IRC safe network and add this Minkowski function information, then it comes very close to the CNN classification result. And when we added this Minkowski function information, the Minkowski function CNN result also improve significantly, and the calculation time reduces and the conversion time reduces. So this means this Minkowski function is a very efficient way to express the soft particle distribution without using a bin by bin informations. By the way, I can also tell you that this system converges much faster with a smaller number of events. So if you have some anomalous feature, want to study some anomalous feature by the real data, there will be a certain merit to use this kind of things together with the IRC safe information to save both time and the stability of the classification. So because it is very close to the end, so I want to summarize my talk. So we are currently working on LHC, and we are going to have a high luminosity LSD. So there will be more data in the high energy tail region, and the boosted object will be more important. So deep learning allows us to utilize multi-correlation among the jet variables, and even through reconstruction using this QCD feature like jet rapidity gap and kind of things will be more important. And the current success of LHC is based on the deeper QCD understanding, and that I think should be true for jet physics. And there is more interesting application of deep learning than that will be described by Tillman. So that's the end. Thank you.
Okay, thanks very much for the talk. So any question from the audience? Okay, so there's one question.
I have a question regarding this standard set of jets. These are Monte Carlo jets, right?
This one?
Well, but everybody uses for this jet the stop tagging evaluation, how well they work. These are Monte Carlo jets. Did anybody try to compare what happens you train on, I don't know which one it is, Pythia or whatever, train on Pythia and then make it operate on Herbig or vice versa?
Oh, I did that.
How much degradation does one get?
Well, the PCR classification works actually much better than Helwig. And the real life is between PCR and Helwig. And I have one exercise by myself. Actually, you are talking. This is I'm very happy because you are asking about my skipped slide, and so this orange dotted line is I trained the network using a PCR and feeds a Helwig event, and then if you go this way, the network result is more like top. And so you can see that the Helwig find the PC this network find the QCD, some of the QCD event is very much top right. So this is a kind of problem, and I have an answer to that. So I can rescale the Helwig event by using so that this Minkowski function distribution is very close to the Pythia one by that we can do very easily by reweighting. And once I reweight this, then you don't have this peak anymore. And I do this reweighting only 2 Minkowski functions, and I'm working on the higher dimensional Minkowski function reweighting with my collaborators, and you will see that if it could be better or not. This is actually a kind of interesting to do.
Thanks.
Yeah.
Okay, so yeah, because of limited time, so we go to the next speaker. So let us thank Mihoku again for the talk, and yeah. Okay, good. Okay, so our next speaker is Tillman Plan. So here we talk about generative networks for the LHC. Tillman, please start. Yeah.
Thank you very much, and thank you very much for having me. I changed my title slightly because Mihoku already had plenty of QCD in her title. So Mihoku and I coordinated that she was talking about classification. I would talk about generative networks, which, both of them have to do with QCD and with new physics, hopefully. So let's just remember, the LHC goals, which I don't have to say that at this conference, that, we're asking fundamental questions about physics, and that includes new physics beyond the standard model. And that has to be there, and we know that because dark matter is just not part of the standard model. And then on the other hand, on the experimental side, what experimentalists show us is these beautiful pictures of precision measurements of all kinds of processes, like TOPS, gauge bosons, anything, jets, with vastly different rates, high precision, and super excellent agreement with theory. My only problem is that these measurements are utterly and totally useless. And because if you want to find new physics, and this is what we are after at the LHC, I don't care about measuring Z plus jets. I care about finding new physics. Kinematics is all we care about. And that tells us something about the challenges, namely the simulational challenges for the LHC. So what we do at the LHC and what we are going to do more and more is what some people call a simulation-based inference or likelihood-free inference. And this is essentially, we start with the Lagrangian, we calculate some scattering and perturbative quantum field theory, we simulate events with detectors, and then we have event sets that we predict corresponding to a certain theory, and then we compare those event sets, or the kinematic distributions or kinematic patterns if you want. We compare those with the actual measurements. And this is essentially a data, big data driven analysis chain. Notice it's not actually data driven because it's actually a simulation based, it's a theory driven, if anything. Chain. So here you see the simulation chain that goes from theory to scattering, hard scattering, QCD shower, fragmentation detectors to events. As Mihoku alluded to, never forget the fragmentation and the detector effects when you do LHC physics. And that is going to be a problem because for the high luminous LHC, we have to prepare a roughly 25-fold data set of what we have now. And that means we have to simulate many more events than we have now with much higher precision than we have now. We have to essentially go to like 1 or 2% or even below the percent level in simulations, which is a huge challenge. And at the same time, we have to keep our signal hypotheses flexible because we want to test all kinds of new physics and we don't know what that new physics is going to be. And like, it could be light dark matter, heavy dark matter, WIMPs. You ask Carlos Wagner gave his talk here, like, so like you can ask all kinds of people of all kinds for all kinds of signal hypotheses, and they change with time. So we have no idea what we will be looking for in 10 years from now. And then on the experimental side, you also, anybody who has ever looked at this analysis remembers that, the more precisely you measure, the more you depend on relatively low rate, high multiplicity backgrounds, like this typical single top plus a couple of jets plus a lepton plus maybe a bottom or something like that. And this is a challenge in simulations. And these simulations are a key ingredient to all the inference that we want to do at the high luminous LHC. And this is basically where we stand. And this is where we hope that machine learning can help us in 3 ways, as far as I can see. Like, first, we expect to machine learning to improve our current tools, that call them MySherpa, ML-MatGraph, whatever, like, improve the current tools to get better. Then we will develop new tools, like, for instance, fast ML generator networks. I'll show you something about that in a second. And then, as a theorist, I of course hope for like some kind of a conceptual progress, like, something new, like, and I'll show an example for this is invertible simulations, but then there's also lots of modern inference techniques that we can develop using machine learning for the LHC. I'm not going to talk through, like, about all the stuff that has happened in the last year or two even on generative networks. This is just a linked list here. Hyperlinked list of papers if you want to look and understand what's happening in the field. Here's like a bunch of papers that I came up with, and this is starting from fundamental basics of machine learning, where particle physicists are by now trying to contribute something useful to of course jets, super resolution. Mihoko mentioned that super resolution means using generative networks to improve jet tagging, phase-space simulations, detector simulations, event simulations, event subtraction, and event unweighting. Event unweighting being currently the big bottleneck of hard matrix element simulations. Unfolding, a big experimental aspect I'll talk about later. QCD factorization, EFT models, inference, actual inference, measuring stuff like QCD splitting functions or whatever you want to measure. Using modern methods in jets or events. Pattern densities, we all know pattern densities. NMPDF has been the first neural network application to LHC physics, and then more recently also uncertainties that I'll talk about in a second. But just give you an idea what the standard stuff is that we do these kind of applications. So for instance, we look for TT bar production. So we look at generating events for some kind of hard process at the LHC, and that could be TT bar with 2.6 jets. That's interesting because it has lots of narrow on shell structures, right? You have the T and the T bar being on shell, and you have W and W plus and W minus being on shell. So there's lots of intermediate mass constraints. And then there's N jets or W of Z plus jets, where the challenge in simulating that stuff is a variable number of particles, or the topology from jet-jet separation, because if you have several jets, these jets cannot be arbitrarily close to each other. So your phase space actually has holes. So there's a proper topological problem when you look at the phase space. The phase space doesn't have a naive topology if you look at multi-jet production. And just to give you a flavor of what we've been doing, for instance, in our group, but many other groups are doing the same thing. This is using normalizing flows, or what in Heidelberg we call an INN, invertible neural network, that we use to simulate these events. You basically train on events, and then we have a mapping into a latent space, and we sample from the latent space, from a Gaussian latent space to be specific, into the physics space. And if you learned that relation, you can actually sample events several times of what you had in the training sample. And here's some example. The goal, as I said, call it 1% precision on the density, the underlying density when you bin stuff. This is PT of the leading jet here, and you see here we have deviation truth over model, a percent level. This one here is eta of the second jet, works fine. Delta phi of the first and second jet works fine. The reason why the paper isn't yet published here is like, delta eta of Jet1 and Jet2. This is exactly that topological problem. And we find that our network still has some issues learning those topological structures, which is a known problem for normalizing flow networks. And then even like, when you go to, for instance, the delta phi of Jet4 and Jet5, what you find is that the network, even in the presence of very limited statistics and large statistical uncertainty, still learns the structure quite well, given the statistical fluctuations it has to live with. So this is currently like, one of the things that people have been doing. It's a relatively standard task, essentially similar TT-bar, right? Using a neural network, or simulate multi-jets using a neural network, depending on what you want. What's more interesting is doing something that in principle we all want to do, but it's actually very hard in the standard tools that we've been using. And that's invert LHC simulations. So call this inverting a simulation or call this unfolding. So what we want and what we do actually is, for instance, we unfold the QCD shower to a hard parton. That's certainly standard, it's called a jet algorithm, right? Mihoko talked about that. It's exactly like, just an inversion of like, if you think the forward simulation process is turning a parton into a shower, the backward is like, just the inversion of it. Unfolding detectors is quite common in LHC physics. I mean, like, you look at like, just plus missing energy or something like that. You get some kinematic information from detector unfolding. Those detector unfolded measurements are extremely useful for like, theorists to apply to their favorite models. In the top group, and I think it's mostly in the top group, the LHC collaborations are also unfolding top quark decays in this, because they think, well, I mean, in the top quark decay, you'll probably not find like, a new physics, because we have tested that. Well, this is an assumption you can make, and some people don't want to make it, but you can make that assumption, and then you can look for new physics and TT-bar production, where you actually look at the full momentum of the top and the anti-top. And then we all know that the matrix element method for hypothesis testing was like, kind of the ultimate goal of like, inference. And even at the Tevatron, people thought about this, and this was something that is essentially just like, inverting like, your event kinematics to the hard process. And I think it's fair to say that this is something between super expensive and impossible to do. And that is just because forward simulations of Monte Carlo, inverting Monte Carlo simulations is extremely hard. It's in principle possible. It's in a reverse problem, you can solve it. However, it is extremely hard numerically, because every like random number you call, like, you have to like, basically do an unfolding step. So it's in practice extremely hard. Neural networks, on the other hand, if you think about it, like, they work forward, and if you have the appropriate neural network, like a normalizing flow network, you can make this network invertible. So like, why not just use neural networks to like do a forward simulations, which we know how to do, and then do a backward simulation to like, whatever level that you want to analyze your events at, like, for example, TT-bar production at the level of T and T-bar. And this is like, my little graph here, like, forward simulations, we know how to do. Inverse simulations, we know we should be able to do, but it's extremely hard for standard methods, and it's easier with new methods. So one of the ways of doing, one of the ways of doing that is using a conditional approach. So here's the task. You have like, essentially you're mapping, say, parton level and detector level events onto each other, or to each other. And then you can say, okay, like, whenever I see a detector level event, I move that like, into the parton level regime through a connection of the two like spaces that I have learned. That's fine. You can do this. It actually works. It's no problem. The problem with that approach is that you do that once. I mean, you map like, a detector level event onto the parton level side of things, and you get an answer to that. But you have no idea what that answer means, because this is not like, some kind of a simulation, like a Monte Carlo simulation that gives you a probability distribution in parton level phase space. It just gives you one point. And the next point choice gives you another point, and we have no notion what that means on the parton level side. So we have to slightly modify our setup. So what we try to do is we train our setup such that it understands the mapping from parton level to detector level forward, just like we would normally do. But then we're asking a different question. We're now asking the question, how can I generate, given one detector level event, how can I generate a probability distribution at parton level phase space from random numbers? So now here you see I go from the random numbers to the unfolding parton level phase space. So this is the loss function. The loss function of this network is particularly simple and easy. This is we learned from Ulrich Köthe and friends here in Heidelberg. This is just the likelihood that you write down. You might basically minimize the likelihood function here. So what do we do? Like for instance, you take the hard process, ZW production, Z goes leptonically, W goes to 2 jets. So you have like some things to play with, a bunch of mass peaks to see what they do. So, and you're asking, how does the parton level event look if I know what the detector level what kind of detector level event has been measured? And of course, this is going to be like, your network is going to be trained on a model, but this is clear because like any network or any Monte Carlo, anything you do has to be trained on a model. I mean, there's no such thing as a model-free kind of way of training that. Your forward simulation has a model, your backward simulation has a model. The only question is how critical is this model? How dependent are you on the model? And you can test that. Any case, so like if you invert the detector effects, this is just an example here. This is ZW production. The left-hand side, you see the transverse momentum of the second quark. So what you see is parton level truth is the dashed blue, parton level, and then you go to the detector level, what we call detector level truth here, simulation in green, and then you apply a network, and that turns the dashed green into solid blue, and the solid blue is expected to be as close to the dashed blue as possible. If it does that, then the network inverted your stuff, and you see it does. Something more challenging is the mass peak of the W. So you start with dashed blue, then your detector turns that mass peak into a cow pie in dashed green, and then your unfolding of the detector effects resurrects the mass peak, just like it should. Works fine. Of course, as a theorist, I'm also interested not just in inverting the detectors. I'm actually, I should say, I'm even more interested in inverting something like QCD jet radiation. And I know actually, Miyahoko, you had like an old paper with Brian Weber about that. So like, how can I tell, like, which of my jets that I see in an event is jet radiation is just like, parton shower, and what is the kinematic of the underlying hard process? I can ask that question with the network, right? I can do exactly the same thing as I do for the detectors. So again, I start with like, on the left-hand side, 2 jets inclusive. This is parton level truth is dashed blue, and then the detector truth, including QCD jet radiation, turns this into the green dashed, not that big a difference, and then reconstruct the solid blue, and that's fine. Like, it does what it should do. It gets more interesting if you look, for instance, to the 4 jet events. Remember, we only have 2 jets in the hard process. So 4 jets are those events which have the 2 hard jets ideally and 2 additional parton shower jets. So I start from the parton level truth blue dashed, and then the detector truth is for the leading jet here for Q1 turns that into the green one. This is an effect essentially of the parton shower on the hard process jet. So the parton shower generates 4 jets out of 2, and the leading jet turns from blue dash to green dash. And then I move things back.
Tilman, your slide is still LL jet. Is that okay?
Yes.
Okay.
The 4 jets are essentially 2. So you have 2 hard process jets. Thank you for clarifying. I have 2 hard process jets, and I have 2 more, or up to 2 more parton shower jets. So I get rid of those. So I have at the detector level, if you want, and after parton shower, I have 4 jets, but my hard process has only 2. And I'm asking the question, Q1, my leading jet, how does that look if I find it and I remove all the effects of jet radiation? So I get rid of the parton shower that way. I know what the hard process is. And then you can ask, how good is this? Well, you can, for instance, check, like, you never put in momentum conservation. You can ask the question, okay, at the 2 jet or 3 jet or 4 jet level, like, how good is my energy momentum conservation in the transverse plane? And you see, like, on the x-axis, you see the events, and there's like 0.5, 1.0. Okay, like, that doesn't look too impressive until you see that times 10 to the minus 4. So our network learns jet momentum conservation almost perfectly. last question about this one is the statistics of it. So if I now take a single parton level event and I a detector level event and I unfold into a parton phase space many times, in this case 3,200 times, I get a distribution, and that distribution is going to be distributed around the parton level truth. And you see, like, you know, look at the CINN, the blue central blue curve, it's around the parton level truth. Of course, this is an image I chose to do that. Other methods, the FC GAN or the EINN, which I just described, just the EINN moving between detector level and parton level directly, give maybe a distribution, maybe not. What nobody gives is a distribution that works right. So now I can do for a calibration, I can choose a certain number, 1500 detector parton level event pairs, and then I do the unfolding 60 times. So for each detector level, I get a distribution, and then I can check in terms of quantiles, how often does my correct parton level event sit in the different quantiles of my detector level inverted events. And this is what's shown here in the curve. Quantile PT of the QOC1 is, like, you know, where it is in the distribution, and the fraction of events is how often does it appear there. And that should be a diagonal. It should, like, be right straight up, and it does. So this here, now what we have here is a perfectly fine, reconstructed and calibrated, automatically calibrated probability distribution in parton level phase space. So what we've done is we've solved the inverse problem behind unfolding, including a complete calibration out of the box, which I think is very nice and something that people haven't been able to do before. I mean, we have done part of these things, but we haven't been able to do them before. Like, two more things I want to show very fast. First of all, one number is not a prediction. Now, we always tell this to first-year students, and that's true. So, like, you know, I can ask the question, like, you know, what about uncertainties? Like, you know, how can I, like, you know, quantify uncertainties if I learn, like, you know, a distribution? And in principle, I can do this. I'm not going to go into details here, but the tools we're using is Bayesian networks. The Bayesian networks are essentially networks where every weight in a deterministic network now is allowed to assume a distribution, a weight distribution, and then you sample these distributions of these individual weights, and then you get a distribution sample for the network output. So the network doesn't just describe a function, it describes a function and its uncertainty. Or over phase space, you learn a density, phase space density, and you learn an uncertainty on that phase space density. And I'm showing this here for our INN. This is an interesting thing. So this is essentially just, like, you know, a two-dimensional distribution. In one dimension, it's trivial, the same, and the other one is either, like in our case here, it's a ramp, kicker ramp. It's a quadratic ramp. What's interesting here, and we can, like, you know, ask me about that, but, like, you know, it's what interesting is the second panel, because if you look at the absolute uncertainty that you learn here, it has a min-max structure. And normally it shouldn't have a min-max structure. Like, normally it should, like, you would learn with the statistics of the corresponding phase space region. And the point is, these INNs don't do that. These INNs don't, like, do the phase space density scaling of the uncertainty. They actually have a distinct min-max pattern, and that can be explained to the best of my knowledge. The best explanation, at least we know of, is that it really works like a fit. It works like a fit, and if you do a constrained fit, then you will also find that you get a min-max structure on the events in a quadratic curve. So we understand a little bit about how the network learns. For an LHC person, it's much more important that we get the error bars right. And here you see, for instance, it's just a simple Drell-Yan process. And to the left-hand side is the energy of the positron, the energy of the positron. You see from the agreement, the lower panel between the network and the data, you see that the training data is the red, and it like develops in the tail, it develops statistical uncertainty as expected. And you see that the blue network result, including its uncertainty, the shaded region, actually develops exactly the same kind of pattern. What we see in the beginning to the left is essentially a slight mismatch in the position of the peak, which you typically get from this, like the structure, and you see that, like, it also that you see an increased uncertainty there. And so essentially what we find is these uncertainty works. And to me, this is a key step. I mean, as a theorist who works on simulations, this is a key step in neural network simulations. We can't just do 1%, as I tried to show you, but no, we can do uncertainties. Okay. Let me use the last 2.5 minutes on something like to follow up that Mihoko started with. I'm almost done. And 1 second, this is my last slide. And it's about symmetries, because I think this is just like very fitting for the SUSY conference to talk about symmetries and something that people have done recently. So symmetries are a key concept in particle physics. And here's like some results from like Veronica Sanz and Gabriele Marmon on like symmetries, analyzing their particle physicists, but they're still like their art, and they analyze the symmetry structure of paintings. This is like, Monet versus Picasso. And you find certain symmetry structures, O2 symmetries, like translation symmetries, like discrete and translation symmetries, and Z2 symmetry in the paintings of, I don't know how many people have done that. And there's lots of papers that, like, people have thought about, where people have thought about symmetries, and like some of them Mihoko already mentioned, like, around symmetries, permutation symmetries. These were these great graph networks, and then recently attention transformer networks. So what we've done recently, like, the last thing we've did here with my postdoc, Barry Dillon, is, for instance, at anomalies searches, we know that we want to map our physics space into the latent space. This is just the same storyline that I had just for these INNs, like, one space into the other. And now the question is why should it be easier to do my analysis in physics space and in latent space? Right? If I map everything nicely, I could map it such that my analysis is easier in latent space. And possibly the Lund jet plane is such an example where things get easier if you look into the right latent space and then you do your cuts there, right? So when you do that, what you want to ensure is that you have a set of known symmetries, and under those symmetry operations, like, all the, say, jets or events which you can generate from these symmetry operations end up in the same point in latent space. And this is the symmetries that we have at the LHC in jet physics: is rotation, translation, permutation, augmentations, collinear merging, soft noise, or what Mihoko called soft collinear safety. And this is just one illustration. This is for rotation. You're looking like, you're rotating your jet image, and you check how similar the position, or like how close in position this image ends up in your trained network, close to the original before rotating. And you see here to the left, this is without learning rotation, and green is with learning rotation. You see that, like, that helps, right? I mean, we basically get arbitrarily close. So S is the similarity measure. It should be 1 if everything is identically mapped. So what we find is that it's possible to do that. Specifically, technically, you can do this using self-supervised learning, something explicitly done in energy flow polynomials, but we do this implicit through self-supervised learning. So we just like learn from a combined sample, and we can test that by through a simple classifier test that I don't have to go into. So to check if this really is a difference, and of course, my favorite application is top tagging. What's important here is that, to me, like, this is like a theory thing, right? I mean, all of a sudden, like, like we have all these tools, and as Mihoko said, like, at some point, theory wants to understand them better. And one of the ways to understand things better is put symmetries into these machine learning tools, and put symmetries into the latent space. And with that, I'm done. Talking a little bit about symmetries at the SUSY conference. So machine learning is by now standard in classification, regression generation. Everybody's using it. Like, a lot of people are skeptical, but everybody's using it. And the reason why networks are so great is because they're the best available interpolation, and they're fast. GANs, generative adversarial networks, are the cool kid, but I really like these inverse networks, these flow networks. Precision is still an issue. Reliability is crucial if you want to apply stuff. And uncertainties we can do now. And symmetries, I think, is the future playground. If you want to, like, of young people, if you want to play with something, think about symmetries in machine learning. By the way, I'm not the first person to come up with this. Is Max Welling. I think if you look, he's a famous machine learning guy who also happens to be a Tufts student. You can actually read his papers and learn a lot about symmetries. But no matter what, like, we need, if you want to make progress in that field, we need new and we need fun ideas. So go get cracking. Thanks so much. I can't hear a thing. Emmanuel? Can I share my...
I have a question regarding this inversion stuff.
Yes.
Always you assume that you know what the underlying process is. So of course, real life, at least in SUSY conference, real life, a good part of your events will actually come from chargino-neutralino production and have a couple of LSPs. So it looks the same, of course, for the visible particles. So what happens if you try to invert those? Will your network tell you that this is not invertible, or you're trying to invert the wrong program? Process, or is it just give you something which is completely fictitious?
Well, no, what we found, like, we didn't check it for this session network architecture, we checked it for another network architecture, and there's another paper by Ben Nachtmann. So what it does is any event will be like any event after detector will be mapped onto a phase-based configuration, and if everything goes well, the same mass peak that exists there, like the SUSY mass peak, will also exist after mapping into pattern level phase space. So you would hope that the mapping of the two phase spaces keeps track of the kinematic patterns that exist.
May not actually be physically just, I mean, at least at the pattern before radiation, your Z and W have to be back to back in this process here, right? And the chargino-neutralino not. So if they aren't, what happens?
Oh, if I do something,
network, of course, but what will the network do?
Yeah. Oh, so
okay, or what?
No, this is an excellent question. So because that brings me to the symmetry, right? So what I have to do here is, when I define what my hard process is, I'm defining an underlying set of symmetries, as you would say, like, back to back essentially. So in that case, what would happen is that you would get some weird results for 2 to 2, and then you would have to go and you would check, well, why don't I define my hard process to be 2 to 3, and that will look different, and look, it'll fit better, and it will reproduce the charginos. So or how many other particles you have. So, like, what happens is the hard process I define, that's my choice. I can define this however I want, right? I mean, to what I map, nobody tells me what the hard process has to be. So the number of final state particles, I should like, the number of degrees of freedom, it shouldn't be too small, because then you get additional symmetry constraints that your mapping cannot fulfill because they don't exist in your data set, and you get weird stuff. And the moment your assumption is broad enough that the network can actually accommodate it, then you're fine. Then it'll actually reproduce the kinematics right. Or otherwise, Manu, you have to give the network the space to express stuff. If you over-constrain it, it's going to give you garbage.
I want to give you garbage anyway, unless you tell it that to actually looking at chargino-neutralino production, no? How else is it supposed to know?
Because the network learns proximity in phase space. It's not just, it doesn't learn, if you think about it, if you give it like, n particle in the final state, it actually learns proximity in phase space. It learns phase space structure before it actually learns like where a mass peak might be. So these networks, they map spaces onto each other, right?
Yes, but they learn from the simulation, and to realize it's not a simulation. But wait, I think we should stop this now.
Yeah, we can talk about this. But so the answer, I think the answer is, it learns two things. It learns the simulation, the details of the simulation, but before it does, it learns the idea that there is a phase space, like a metric, if you think. And that should be enough to maintain, to keep your physics. If you look into the GAN unfolding paper manual, you'll see that we reproduce a Z mass, a mass peak in ZW production. It stays.
Good. So yeah, you can discuss offline. I was muted, so sorry, I was muted. Okay. So any urgent question to ask? If not, let us thank Tuma and Plan again for the next talk. So we will move to the next speaker. Thank you.
Thank you.
Yeah.
Hi. Okay. Let me. Can you hear me? Let me start to share. So.
Sure.
Oh. Yes.
Yeah, we can see it, but not in full screen.
Is it full screen now?
Yes, it's in full screen now. Yes. Okay, very good.
Okay, sorry.
Okay, so yes, so our speaker is Kino Isidoro. So he will talk about B physics anomalous and flavor hierarchies and natural link.
Okay, yes, it's a pleasure to be here, and actually my talk will be a bit different than what you heard so far, and no SUSY at all, and not even much collider physics, although maybe toward the end. But on the other hand, I think hopefully real data, because I'll discuss something connected to this interesting observation that we see already since quite some time in B physics. So let me start with some very general, so this is the plan of the talk, but general consideration. Of course, here in this context, I think we all agree that the standard model is only an effective theory and there is something above. So we think that it's there should be some UV theory from whose low energy limit is the standard model, right? Now, all our effort are in trying to understand which is this completion. So we want to go from the standard model EFT up to this UV theory. Now, before looking at the data, I mean, let me say a few general things. I mean, since we have not clearly seen any high new degrees of freedom at high energies, what we can deduce from the properties of the standard model EFT in terms of high energy. But there are two classes of information that I think we can deduce, which are very valuable in determining the UV theory. One thing is possible violation of accidental symmetries. That is, okay, when we build this effective theory, if we identify some higher dimensional operator that violate the symmetries, the accidental symmetries of the low energy part, clearly this will a natural and powerful link to some new dynamics. This is really a quantitative hint. But on the other hand, we should not forget that even if you look closely to the structure of the dimension 4 Lagrangian, the unnatural aspect of the standard model coupling are also a very important indication of a very important guiding principle toward the UV completion. This, of course, is more qualitative, but is still very important. So let me be more specific on what I mean here. So violation of accidental symmetry, I guess, is something very familiar to all of you. Now, if there is a theory, a fundamental theory that doesn't have as a different symmetry structure than what we see at low energy, is natural. It's very possible that at low energy we have some enhanced symmetry. And this is, for instance, the case in even the standard model. If we go to a low energy, if we forget about the weak interaction, we have a big flavor symmetry. This is simply because at low energy we can write, from a point of view of effective theory, we can write a small number of operators, and this operator accidentally conserve symmetry. Again, well-known example is Bayer number, lepton number in the standard model, right? So searching for violation of accidental symmetry is a very powerful way to identify something that maybe occurs at much higher energies and is very tiny, but then you see it because it's a violation of a symmetry, and you see it also at low energy. Now, what I try to show you in the rest of this talk, I mean, the violation of lepton flavor universality that we start to see in BT case are exactly of this category, okay? Okay, this I think it's a well-known fact, but I want to link this to the other aspect, that is the unnatural aspect of the standard model couplings. As you know, the standard model Lagrangian has two pieces, the gauge and the Higgs sector. The gauge is very natural. I mean, we have three natural coupling of order 1. Is the Higgs sector, which is not natural. And I think the Higgs, I mean, we are all convinced that the Higgs structure contains some imprint of its UV completion. And these imprints are there in the coupling, which are the Higgs mass and the Yukawa coupling. And I mean, the Higgs mass, this has been discussed for ages, so I don't want to spend too much time on that. But let me, on the other hand, point the unnaturalness of the standard model Yukawa coupling, which is a different type of unnatural. They are technically natural, but still they are peculiar, because we know, I mean, that the Yukawa coupling are not all of order 1. They exhibit a very hierarchical pattern. We have one Yukawa coupling, which is 1. All the other are much smaller. These are 3x3 entries. We have 3 of them. You know, we have this hierarchical spectrum, the hierarchical mixing structure. Clearly, this points to some non-trivial dynamics from the point of view of flavor at high scale. So I would say that when we look to these Higgs Lagrangian, we deduce two general things, okay, from a point of view of an effective theory. There is the well-known hierarchy problem that tells you that there must be some new physics not too far from the TV scale. at least coupled to the Higgs and to the top, which are the couplings, the largest dominant coupling here in this sector. But at the same time, we also have another indication which is not related to a scale, but is related to non-trivial dynamics in terms of flavor, because the hierarchies in the coupling describing Fermi mass tells you that there should be at some scale, we don't know which, but there should be some non-trivial flavor dynamics. So dynamics that distinguish the different generations. This is clearly an imprint that we have in our Lagrangian. When we put in new physics model where treat all the fermions in a universal way, we are clearly kind of omitting this information, which on the other hand is there in the Lagrangian. So what I will try to argue in the rest of this talk after this general introduction is that the violation of lepton flavor universality, also the hints that now come from the higher dimensional operator describing the data in B physics, are possibly telling us that we have to tackle these two problems together. Not only care about the stabilization of the Higgs, but also care about non-universal dynamics. And this is something different than what we've been done at least till a few years ago. Okay, so first, now let's, after this brief introduction, let's look at the data, the anomalies, these B anomalies. So since already now almost 10 years, result in certain BDKs exhibit some tension with the standard model prediction, which are connected to which seems to indicate a violation of lepton universality. So we seem to observe a different behavior beside pure kinematical effect of the different lepton species in two types of process. One is B2S-LL, where we compare muons versus electron, and the other is B2-char lepton neutrino, where we compare the tau versus the light lepton. So what is lepton flavor universality? As anticipated, lepton flavor universality is an accidental symmetry of the standard model Lagrangian. Actually, is an approximate accidental symmetry. It's not even an exact one, because it's broken by the Yukawa coupling. So it's a symmetry that we have. So the fermions couple universally if we switch off the Yukawa coupling. Indeed, lepton flavor universality is badly broken in the Yukawa sector. You see here the three Yukawa coupling that go from 10 to minus 6 to 10 to minus 2. However, all of them are very small compared to the gauge coupling. This is why in first approximation for the dynamics and not for kinematics, we can forget about all this Yukawa coupling and treat the leptons as a universal, with universal dynamics, which is what we usually refer to as lepton flavor universality. But you see clearly this is just an accident. It's specific to the gauge sector of the standard model. Indeed, the first things that could violate it, that is the Yukawa, violated very badly, but still with an overall size that is small. But beyond the standard model, we can have new interaction that violate it in a much stronger way. And this is what the data seems to indicate. So let's now look closer to the data. So let's first concentrate on this B2S, the neutral current anomalies. So here we have several observable that all point to the same type of dynamics. Some of these observable, for instance, the P5 prime anomaly is related to the angular distribution of B2K star mu, was the first historical to be observed. This is difficult to discuss because there are a lot of hadronic uncertainty. Also, the branch ratio are more complicated to discuss, but then what now drives the significance are these lepton flavor universality ratio, so the ratio between mu and the electron rate in B2K star and B2K decay, where the theoretical error is very small. And at the same time, also, we see a smallness of the branch ratio of VS mu, which is also something that we can which we can control theoretically quite precise. So, as I said, some of these observable are affected by a long distance effect, others not. And why we are all excited. I mean, I was excited already since several years, but recently there has been more excited because of a new result that strengthened the significance here in this ratio RK, and now which alone is a 3 sigma effect. But the picture, this 3 sigma, if it was only this 3 sigma, you can forget it. What is really nice is that it's not only this 3 sigma, there are a lot of different effects which all point together to the same type of dynamics. And how we describe these dynamics, okay, just in one slide, to describe this effect within and beyond the standard model, we have to build an effective Lagrangian describing the B2S LL transition. We have two types of operator, the point-like BS-LL coupling, axial current, vector current, or also have the 4-quark operators. These operators here are those that we can whose matrix element in non-leptonic process is well understood because it just is a form factor effect. So this is what I call easy and clean. This is the complicated part of the problem, because if we have, for instance, B2S charm operator, this effect, okay, we have the rescattering of the charm, and then when this is clearly non-perturbative in some region of phase space, because we can have the charmonium resonances, and if you attach a photon, you produce a lepton pair, you affect this rare process. However, you see this type of dynamics, which is the one that we don't control very well, can only make a universal effect, so the same effect in electron muons. No way to distinguish electron muons by this type of long distance dynamics. And also you can only affect the vector type coupling. This is why we say effectively these dynamics can induce a universal shift in C9, which is the effective coupling of this operator. You cannot affect the axial current operator, and you cannot make a difference between electron muons. So this is why this long distance effect, we've been discussed for years, keep the LFU ratio as clean, because they cannot affect this ratio, and also cannot affect PSP mu, which also remain clean. So let's look at the clean observable only. The clean observable are summarized here very briefly. We have this R ratio, and you see here the three independent measurements. So we have the measurement of RK star at low Q square, RK star at a higher value of Q square. Q square is the lepton invariant mass, and recently the latest RK result. All of them, you see 2.1, 2.5, they all are more than 2 sigma, and one of them alone is more than 3 sigma. And in addition, there is BS mu, which is another 2 sigma deviation. So all of them is an interesting, consistent set of anomalies, which also goes together with the other anomalies for which there is more uncertainty. But if we just keep this alone, and I try to fit the data, you see this is what we get, trying to fit the anomalies in terms of modified Wilson coefficient for this simple point-like operator, with a conservative fit, just fitting the difference between electron muon coupling, we get a 4.6 sigma significance and a nice consistency between the different measurements. If we put on top the other observable, the significance goes well above 5 sigma. Okay. Of course, here we have to be more careful because we are sensitive to charm scattering. So this more than 4 sigma, I don't even quote a number because it's difficult to say precisely how many sigma are. But still, I think it's clearly a very high significance, and there is a nice consistency between the two sets of measurement. And recently, also, we did a very skeptical approach. Okay, so here I am assuming that mu physics affect only C9 and C10, which are the operators which I think should be affected by mu physics. But we did a more general analysis, allowing all the operators to be affected by mu physics, allowing the most general structure for this charm loop, and still we get a 4 sigma significance. So the effect is really significant. What these anomalies are telling us now, again, being back on the interpretation, trying to interpret these results. So we clearly have an evidence for new type of operator of this type, where you have couple quark to lepton. Actually, I write it here in this non-standard format for a reason that will be clear later on. But so clearly an operator that connects 2 quark and 2 leptons, so a BS and 2 muons, and affect the muons, not the electrons, with a strength which is 10 to minus 5, or few 10 to minus 5, the Fermi coupling. So it's a super weak interaction. It's a small effect. No surprise that we have not seen it elsewhere, and with a specific left-handed structure. This is actually the precise information that we have here. The less precise information is this modification to the universal C9, which is partially polluted by the charm, but doing our best, we can still get an information here. That you see this is not different from 0 more than 2 sigma, but still this is interesting, and we can interpret it exactly with the same type of operator, but now instead of having the muon, having the tau here with the larger coupling. Then if we close the tau loop, you attach a photon, you modify electron mu in the same way, and it's nice. So it seems that what we seem to see from the data is a pattern where we have this very clean, precise 2,3 mu operator, very small, a bigger 2,3 tau tau operator, which is roughly, so you see there is 2 order of magnitude difference between this coupling here, because the unit here is 10, the unit here is 10 to the 3. So clearly it's a well-defined pattern that emerged from these anomalies. Then there are the other anomalies, which are the charged current anomalies, B2 char, lepton neutrino. Here again, I don't have time to enter too much into the detail, but there is a 3 sigma excess combined with different experimental results, which I agree very well. I mean, the probability of the experimental, the consistency, it's high, 30%, and the discrepancy with the standard model, it's 3.1 sigma. And if you interpret this, again, you can use the same type of operators, okay, but in this case involving tau. And in this case, could be a combination of an operator of the type 3,3, well, this refers to the quarks, and 3,2, because there is also the CKM rotation in this context here, with the tau, okay? And in this case, the data are less precise, so you don't know if this is purely left-handed, like this curve here, or if there is also a right-handed contribution. But clearly is the same type of operator, same leptonic operator. For sure, you need the left-handed. Maybe there is also some right-handed contribution. So, okay, these are the data in a nutshell. Let's now start to build an EFT that describes this data. So, anomalies for the moment are seen only in this same leptonic operator. We definitely need left-handed current, as I told you, and we need a rather specific flavor structure from the point of view of both quark and lepton. We need something which is big to compete with the standard model 3 level in the B2 char tau process, and this clearly is something that involves many third-generation fields, because we have the B, we have the tau, L3, and the neutrino tau. We need something smaller, competing with a loop amplitude in the standard model for the B2S mu1. But in this case, we have more second-generation fields, so because we have the B, but then we have S, mu. So the idea is that we have something which is big for third generation and smaller for when we involve second generation. And for the moment, we don't have any evidence for effect involved in the first generation. This is really nice because it points to the pattern, which I show you very qualitatively at the beginning of the Yukawa coupling, where we know that indeed, if the Yukawa coupling are determined by some new dynamics, these new dynamics should be coupled strongly to third generation and weaker when we go to later generation. So let's now put the two anomalies together, still using an EFT approach. I told you what we really need is this type of operators. And we have essentially 3 evidences. The cleanest evidence is the one for the B2S mu, which is this up corner here, which is the smallest effect, but is the most clean. And this is this band here. Then again, B2S LL, we were deriving this information on the tau operator, but this tau operator, because of the when you look at the left-handed current, because of CKM rotation, also affect the charged current. So I put the two things to here. In the charged current, we have a combination of this operator 3,3 tau tau and 2,3 tau tau, and there is a perfect overlap between the two type of anomalies, which is fantastic. I mean, these are very different order of magnitude. So you see, this is the biggest effect, and this is 10 to minus times smaller. This is 10 to minus 3 times smaller. So it seems that we have something of order 10 to minus 2, the Fermi coupling, and then we pay a 10 to minus 1 each time we put a second generation field, either quark or lepton. So we have a 10 to minus suppression for each second generation quark or lepton. And recall that this is exactly the size that we have in the Yukawa coupling, where we also put the 10 to minus 2 suppression when we go from third generation to second generation field. And there is a nice consistency between the two set anomalies. So with this type of operator, we describe, okay, if we just look at the anomalies, everything is nice with a nice flavor structure. Now, this is what we see. We also have to discuss what we do not see. We do not see affecting 4 quark operator, affecting 4 lepton operator, okay? And also you see this type of operator, which I told you I wrote in this specific quark lepton current, is a specific combination of this MEFT operator. So it's a singlet plus a triplet. It's not a QQLL, neither a singlet nor a triplet of QQLL, but is a specific combination, which is what you would generate from the exchange of a leptoquark, which is coupled directly to the leptoquark current. So clearly, all this goes into the direction of the leptoquark, because you see the leptoquark as mediator would not generate a 3 level for quark, would not generate a 3 level for lepton, and would only generate specific certain specific contraction of quark and lepton current. Of course, this is just a 3 level structure. Then if we take a MEFT approach, we have to say, okay, suppose that even we generate this at the 3 level by some new dynamics, we have to understand if this is radiatively stable and which are the effects generated beyond 3 level. And here I give you a first hint. Of course, these effects are important. For if you take this semi-electronic operator, you close the tau loop, you generate countercorrection to BB bar mixing, and you also generate unavoidably 4-lepton operator, which violate universality in tau decay. And these are significant bounds which cut part of the region, but there is a part of the region which is not cut, and this is the most interesting one, where the motivated model should somehow end up here. So it's clear that the picture is constrained, but it's not ruled out by the precision observable. Okay, now we clearly, to address these things in a more precise way, you see clearly these loops are divergent, so we have to put cutoff to make the things consistent. We really have to employ models. So how to build the model? Well, we have to address two questions: the flavor structurally now in a consistent way, and the nature of the mediators. Let me start from the flavor structure, which is the idea that seems to emerge from this data. Well, the idea that seems to emerge is a multi-scale picture. It seems that these new dynamics, so here we have the retro scale. The first scale that we should encounter in our new physics model is a scale where we couple to the third generation, and possibly we address the Higgs problem, while we don't couple to the second generation. Then the idea is that the different generation coupled to the new dynamics and higher scale. This justifies why the Yukawa coupling are small, because they come from heavier dynamics, and justify why we don't see higher dimension operator built in terms of the first generation. So it's really different than the old idea of treating the three families as identical copies up to high energy. At high energies, they become really different. They are structurally different, coupled to structurally different dynamics. Of course, if we focus on the first layer here, what we see is indeed our above the retro scale, our SMEFT should be built with an approximate U2 symmetry that is treat the first two families as essentially massless and uncoupled to new physics, except for some small mixing, while new physics affect mainly the third generation. And this is reflected and is consistent to what you see in the Yukawa coupling, where the first only leading Yukawa coupling is the top one. So the Yukawa coupling belongs somehow to the new physics sector, as you naturally expect, being completely different from the gauge sector. Okay, now coming to the mediators, I already anticipated which are the natural mediator for this effect are leptoquarks, for a very simple reason, because leptoquark, so we need something that couple quark and lepton. A priori, you could have a W prime, a Z prime, or even a Higgs, but this doesn't work because then you affect Bisa-based mixing at the 3 level and you are essentially dead. On the other hand, the leptoquark has the virtue of doing something at the 3 level for semi-leptonic, where we see something and nothing at the 3 level in delta effect 2 amplitude or tau decays, where indeed we have strong bound. So clearly are in better shape. Also from the point of view of direct searches, leptoquark are in much better shape. Now here has been a lot of works about which leptoquark we should use to describe the anomalies, and I don't have time. And let me just focus on the most interesting case, in my opinion, which is, you see, there was this nice work by these authors, which try if you want to address both anomalies, okay, which is more difficult but also more interesting, there is only one candidate that emerged as a single mediator, which is this U1 leptoquark, which is the leptoquark of the SU4 group, the Pati-Salam group, and that, as we identified this already in 2015 with Riccardo Barbieri and collaborators, this really is nice because it can have exactly this U2 structure. We can implement it in a natural way, and as this virtue of affecting directly the anomalies and nothing else. Of course, we can build more complicated model where there are more mediators, but they are more tuned. This one is really natural, and as you see, also has a nice UV completion. But before going to the UV completion, let me now do the phenomenology of this simplified model, where I put in the leptoquark, couple it to quark and lepton with the flavor structure which respect this approximate flavor symmetry. These are free coupling. At the end, there are only 4 free coupling, not too many free parameters. I can describe both anomalies. You see here how we describe RD, RD star, and these RK, so the universality in BS LL. These are the data, and this is the prediction of the model. And you see this is the standard prediction, which is far away. On the other hand, is well consistent with the data. we have basically two options, with or without right-handed current for the third generation. Both options are quite good and very different from the standard model. The nice thing is that then the model is completely determined by the anomalies and by satisfying the other low energy data. For the moment, I have not put any single information from high energy data, and so I can predict what happens at high energy. So this guy should be seen at the LSC and should be seen, especially in the high luminosity run, via the T-channel exchange. It's quite heavy. You see here, I plot the coupling versus mass. In principle, there is the pair production, but the pair production is limited in reach. On the other hand, the T-channel can go to much higher, we can explore much higher masses. These are the present bounds from the pair production. This is the present bound from the PP2 tau tau. And you see how the bound will improve. Here, all this region will be covered in the high luminosity phase. And this yellow band is the preferred region by the anomalies before putting the high PT constant. So it's really just around the corner. It's not an artifact. So the preferred model wants to be here. Of course, the part of it has been excluded, but there is a big fraction which is not excluded. And of course, we cannot go much more than 3 because then start to be non-perturbative. And okay, if we look at the right-handed case, a bit more of the model has been excluded, but there is a big fraction which is also consistent. And of course, this model predicts a series of effects in other rare process like tau decays, tau to mu 5. So we have lepton flavor violation in taus. The case of like B2K tau tau should be largely enhanced, and these are within the reach of future experiment in flavor physics. Now, the last few minutes about UV completion. Clearly, this is a vector leptoquark. So vector leptoquark require a UV completion because it's a massive vector field. But there is a very nice UV completion, which is a Pati-Salam, or better, Pati-Salam-like model. Let me first recall you what is Pati-Salam. I guess probably it's familiar to most of you, but okay, it's the SU4 group where we put color together with lepton number. Okay, and so it's a beautiful construction where indeed color emerges the breaking of SU4 to SU3. And from this breaking, you generate exactly the U1 that we need in terms of gauge quantum number. However, the plain Pati-Salam model doesn't work because there is no flavor. So this leptoquark would couple to all the generation and is completely killed by bound from the first generation, for instance, from K-long to mu e, because you will see it here and we don't see it there. So we have to put in flavor into the game. And we can do this in a structural way by extending the Pati-Salam group to, for instance, what are now called 4-3-2-1 model. That is, instead of considering SU4, we consider SU4 times SU3, where color is a subgroup of these two. Okay, exactly like in the case of the electroweak symmetry, we have SU2 left and SU2 right, and then the QED is a subgroup here. So easy, actually, you see, I have the picture here. So in the case of electroweak symmetry, we have SU2 right, or if you want hypercharge, and then there is the unbroken subgroup here. The idea is that we have exactly the same structure for the strong sector. We have SU3 and SU4, but these two groups are flavor non-universal. So this one see the third generation, this one not, okay? But the diagonal, of course, will see the generation exactly in the same way, and this color. This way, this SU4 that contains the leptoquark will couple mainly to the third generation. So it's a very nice construction. This is just a sketch, okay? Then you can implement this in several different ways. Here there are just a diagram to illustrate the various efforts now going on, even model with extra dimension. But the basic idea is this one, that you really have SU4 times SU3, and this SU4, for instance, you can think of it something where you distinguish the third generation and the first two. And okay, here is a sketch about extra dimension. If you want, we can go in the discussion session. But it's really, I think we really have a theory of flavor, which is very nice. Okay, so we really connect this hierarchical structure of the Yukawa coupling and this anomaly hierarchy in the anomalies to the structure of the model. But I want to mention one key point is from the point of view of phenomenology. If we have this 4-3-2-1 model, when we break it down to the standard model, we have more gauge field, not only the leptoquark, more massive gauge field, not only the leptoquark, not only the Z prime, but also a coloron. So a colored, an octet, massive octet, which is a spin 1 heavy particle. This one should couple again mainly to third generation, but like BB and top. But it's a big resonance that one should be able to search and see possibly at LSE. And there's a striking collecting signature, which is PP to top, and you see here the bounds. For the moment, the model is not excluded, but we are pretty there. Okay, so I'm done. I think the statistical significance of these anomalies is really growing, and I think the chance that this is the statistical fluctuation is marginal. And I think these two anomalies really point to some new dynamics, non-trivial from the point of view of flavor, coupled mainly to third generation. And I think it's very interesting, both for the low energy searches and also for the high energy searches. Okay, thank you. Sorry for being a bit over time.
Okay. Thanks, Gino, for the very interesting talk. So we may only have one or two very quick question. So you can go ahead. Yeah.
Yes, I have a quick question. You know, the smallness of bis-2 bunch fraction is mainly driven by the negative results of Atlas. So yes. Assume that finally it's consistent with the standard model. Would this change the picture a little bit? Or?
Well, I mean, we just take the average. We don't make any commitment. Also, if you look at there was the result by LACB, okay, which the central value of LACB is 3, and with an error of 0.3, so it's below the standard model prediction. All the experiments are below the standard model prediction. It's true they are not extremely significant, but they all go in the same direction. So if we remove Atlas result, the overall significance will go a little bit down, but nothing changed significantly. The central value of LACB is also good. It's 3 10 to minus 9 compared to 3.6, which is the standard model prediction.
Okay, thank you.
Okay, so okay, you can go ahead if you want to ask. Yeah.
Okay, it's me. Okay, thanks, Gino, for the nice talk. So I have one question. So far, all the anomalies in the B sector are related to leptons and found in either in the decay rates or in the differential decay rates, but nothing to do with the circulation. How should we understand this? Is this just because we don't have enough precision, or we have to look at the right place?
No, I think indeed this is a very good point, and indeed I don't remember if I have a backup slide. I think B-sub-S mixing start to be a problem. Okay, we should see something there sooner or later, and actually to explain why we don't see B-sub-S mixing, we have really actually to make the model a bit more complicated. So we introduce some vector-like leptons, which actually, this is nice, but still they only if they are in a certain mass region, they need to suppress the contribution to B-sub-S mix. So I think the thing I can say is that new physics CP evaluation should be around the corner, both in B-sub-S mixing, some non-standard effect, and even in D-bar mixing. D-bar mixing is also a very important concept on the model. So for the moment, we predict effect really around the corner for these two CP evaluating observable. So you see, okay, here is not CP evaluation, is the B-sub-S mixing contribution, but you see easily you get a 10% correction to B-sub-S mixing.
Okay, thanks. Probably we.
Yes, thanks.
We don't have time for more discussions.
Yeah,
yes. Very nice talk. Okay, so let us move to the next speaker.
Okay, it's me.
Yes, okay, very good. So you can share your screen.
Yeah, let me share screen. Do you see full screen now?
Yes, now we can see our screen. Okay, very good. So our next speaker is Yue Hongxie. He will talk about fluid physics at HC. Yeah, please go ahead.
Thanks for the invitation. It's my pleasure to present the recent highlights in fluid physics from the LC experiments, including, doesn't work. Include Atlas CMS and HCB. So I'm glad to talk after Gino, who has set the stage and given us the interesting theoretical perspective. So my job is easy. I just need to tell you what the experiments have done in the recent 2 years. So flavor physics has a very broad scope, and apparently I don't have enough time to have everything. For example, I won't talk about anything about spectroscopy or production. I will mainly focus on mixed entity evaluation and the rate decays and the lepton flavor universality tests. And actually, there are dedicated talks on these topics in the parallel sessions. So let's start with introduction to the flavor physics program at the LHC. Flavor physics plays a critical role in answering some open questions related to the nature and origin of the universe, such as what is the origin of matter and antimatter asymmetry in the universe, and is there physics beyond the standard model, and if there is, what is the possible form? To address the first question, we mainly look for new sources of evaluation by making precision flavor measurements and using them to overconstrain the secant measures and checking their consistency. To address the second question, we look for new phenomena in rare or forbidden indices, such as the flavor changing neural current processes, lepton flavor universality violating processes, lepton flavor number violating processes, and probably more. The Large Hadron Collider is a heavy flavor factory with very large production cross-section of BB bar and CC bar. And it can produce all species of B and C hadrons, including both mesons and baryons. The LCB detector is a forward spectrometer with excellent vertex particle identification, tracking, and flexible trigger, making it particularly suitable for CP violation and rate decays. But actually, it can also do a lot of other physics studies, which I don't have time to cover today. B physics is also an important part of the Atlas and the CMS physics program. But they mainly focus on B physics with mu plus mu minus in the final state. So far, LCB has accumulated 3 influence bound data in round 1 and 6 in round 2. And Atlas and CMS have accumulated about 180 influence bound. Okay, let's start with CP evaluation. In the standard model, flavor changing in the flavor sector, in the cork sector, is fully described by the secant matrix with 4 parameters. And particularly, CP evaluation originates from the non-zero secant phase, either not equal to 0. This mechanism can be tested by measuring the angles and the sides of the so-called unitarity triangles and checking their consistencies. Shown here on the left is the unitary triangle correspond to the orthogonality of the first row with the last row. And the right is the triangle correspond to the orthogonality of the first row with the last row. And the LHC is already dominating the measurements of the key observables such as gamma, VTD, and beta S, and is catching up with B factories in the measurements of also VUB and beta. The mixed phase of the neutral BS mesons phi S is equal to -2 beta S, which I just talked about. In the standard model, they are equal. However, phi S is very sensitive to new physics in BS mixing, originating from new particles entering the box diagram. Phi S can be measured in the golden channel BS to JSF phi with phi decay into K plus K minus. The time-dependent symmetry has an oscillation pattern where the oscillation frequency is equal to the delta mass, which is the mass difference between the 2 mass second states, and the phi is the oscillation magnitude. In order to measure phi, or in order to measure CP symmetry, we need to have good flavor tagging performance and the time resolution. The initial flavor of the BS meson can be inferred from the information of the of the particles produced in association with the BS particle, or from information of the decay products of the other B, because BB bar are produced in pair. The decay time of the BS meson is reconstructed using the distance of the production vertex and the decay vertex. The performance in flavor tagging and time resolution for each experiment is given here in this table. HCB has excellent time resolution and reasonable tagging power, thanks to the excellent K-bar separation and the vertex reconstruction. Atlas benefits from new inner B layers, which improves their time resolution from 100 for the second to 70. And CMS recently developed a deep learning-based neural net for the tagging of for the muon tag, which improves the tagging power from a few percent to 10%. However, CMS only triggers on very high momentum muons. Therefore, actually, the overall performance Atlas and CMS are more or less the same. All these three experiments have analyzed the part of the run 1 and the run 2 data to measure phi's in BS-JSI phi. Shown here are the JSI phi mass distribution, where you can see clean BS figures, particularly for Atlas, for CMS and the HCB. And then phi is extracted from a fit to the 4-dimensional distribution of decay time and the angular variables. On the top left, you can see the result of phi's and the decay with the difference delta gamma S from HCB in green, Atlas in blue, and CMS in red. Yeah, you can see that the world average is actually dominated by HCB so far. The LCB result is actually a combination of several B to CC bias modes, including not only JSI phi, but also JSI pi, DS. The world average is given here, where you can see phi is minus 50 plus minus 90 millirad, which is consistent with the center motor prediction from a global fit, which is minus 37 plus minus 1. Another BSDK channel which SCB recently started is BS to K plus K minus. We measure the time dependency P asymmetry from a tag analysis using data collected before 17. So on the left, you can see a clear BS to KK mass peak. In the middle, you see the decay time distribution for initial BS in blue and the initial BS bar in red. And the asymmetry as a function of decay time is given on the right. And from this, we extract the mixed-induced CP violation parameter S, which is different from the other significantly. Therefore, this becomes the first observation of time-dependent CP violation in the BS system. In the CP violation sector, one long-standing puzzle is the so-called K-bar puzzle, namely the measured CP difference of CP symmetry between B plus to K plus pi 0 and B0 to K plus pi minus is about 12%, while based on isospin symmetry, this should be 0. Therefore, there is more than 5 sigma discrepancy. Very recently, HCB improved the precision of the ACP of B plus to K plus pi 0, which is currently the most precise one. And using this, the precision of the world average increased from 2% to 1.3%. And this changes the discrepancy from 5.5 sigma to 8 sigma. So this puzzle is strengthened. Another puzzle in the second sector is the so-called VUB versus VCB puzzle, which is the tension between the inclusive and the exclusive determination of the VUB and the VCB. On this plot, you can see actually the inclusive determinations are significantly higher than the exclusive one. And traditionally, these elements are measured by the B factories using B meson decays, but recently LCB measured the ratio of VUB to VCB using lambda B baryon decays to P mu nu normalized to lambda C mu nu. And this result is illustrated using this origin band, and it is found to be consistent with the exclusive measurement from B factories. Moreover, then we just reported another measurement of VUB to VCB using BS meson decays to K mu nu, normalized to BS to DS mu nu. This time by measuring the ratio of branch fractions of the signal and the normalization channels in two different Q-square regions, in the low Q-square region and in the high Q-square region, where Q-square is the mass square of the lepton pair. And then we determine the ratio of the elements VUB and VCB using the form factors of B to K or B to DS from lattice constant rule calculation in the low Q-square region, or from lattice QCD calculation in the high Q-square region. And the results are compared with the previous LCB measurement and the world average of the exclusive measurement. So you can see the high Q-square value is consistent with other exclusive measurements. Another improvement comes from the recent measurements of data mass using the full run-to data sample. The best channel to measure this is the flavor-specific decay of BS to DS pi. This is done by measuring the oscillation frequency of BS to DS tagged BS to DS pi. So this frequency is related to data mass. Combining the results from this analysis with the previous one, then we get the most precise measurement of data mass, which is consistent but much more precise than the standard model prediction, as you can see. Actually, not only neutral B mesons can mix, neutral chi mesons can also mix. D0 D0 bar oscillation has already been observed by SCB in D0 to K pi in 2013. However, the mass difference parameter X has not been very well determined. Actually, we don't know whether there is a non-zero mass difference or not. In order to solve this problem, then we recently performed a time-dependent Dalis analysis of the decay D0 to K short pi plus pi minus with the full run-to data sample. And the value of X is determined to be 4 plus minus 0.6 per mil. And this is significantly different from zero. Therefore, this is just the first observation of a non-zero mass difference in the D0 mass between the two D0 mass states. And combining this analysis results with the results of D0 to K pi and D0 to KK pi pi, then we update the mixed parameters XY and the CP evaluation parameters Q over P or phi. And the impact of this result are illustrated in these two plots. The blue ones are the constraints from previous analysis, and the origin one is included in this new result. So you can see the big improvement. So I actually don't have time to talk about the very recent significant improvements in two key variables, two key observables, gamma and sin2 beta, which you should go to the parallelization to listen to the speaker. And I just want to emphasize how big impact the HC experiment have on the CCAM global fit. In the global fit, the measurements of different angles aside, from different experiments are put together to obtain the estimates of the four parameters of the secant matrix and check the consistency. So on the left was a case when LGC started 10 years ago, or more than 10 years ago. On the right is more or less the current status. So you can see while all the measurement precisions have been improved significantly, they are still consistent with each other. This demonstrates the success of the secant matrix in describing the flavor changing mechanism. Okay, now we move to the rate case. We mainly focus on flavor changing neutral current B2S plus L plus L minus decays. This kind of decays can be described using a effective Hamiltonian, and the new physics can affect the values of the Wilson coefficients or add new operators. I don't need to talk about this because Gina has covered this. So all I want to say is that this kind of B2SLL decays are sensitive to the C7, C9, C10, and the CS and the CP Wilson coefficients, which correspond to penguin diagrams mediated by different bosons, including photon, Z, Higgs, and Suncells. Theoretical clean observables of new physics in this sector include pure electronic decays such as B2 mu mu, and the special angular observables in the angular distributions. And particularly interesting are the ratio between decay rates of different leptons, such as electron mu and the tau. Let's start with the pure leptonic decay B2 mu plus mu minus. These are very rare in the Stanford model because they are suppressed by helicity suppression and also by gene mechanism and also by secant factors. But they have very high sensitivity to new physics in the rule. The Stanford model prediction of their branch fraction are at the order of 10 to minus 9 for BS and 10 to minus 10 for B0. Many efforts have been made to search for these decays in the recent 30 years. And only very recently that Atlas and CMS have observed the BS decays to mu plus mu minus. And later Atlas confirmed it. And so far there is no significant signal of the B0 decay to mu plus mu minus. Today, what I want to discuss is the recent combination from the 3 LCB experiments using data collected between 11 and 16, and also a recent update by LCB using the full run 2 dataset. So as I said, all 3 experiments have observed the BS to mu mu and have analyzed data until 16. So shown here are the mu plus mu minus mass distributions, Atlas, CMS, and HCB. And their results are summarized in this table, and the average is given here. So from the bottom plot, you can see that the combination result is consistent with the standard model prediction at the level of 2.1 sigma. So we need to use more data to improve the measurement precision, whether there is actually a significant discrepancy or this is just a fluctuation effect. To do this, then LCB recently completed the analysis of the full run 1 and run 2 sample and improved the measurements of BS2 mu mu, but still no signal of B0 to mu mu, so we set a new upper limit. We also update the effective lifetime of BS to mu mu. So here, all I want to say is that the new result still agree with the previous result and consistent with the standard model predictions at the same level as I said. Okay, now I move to the discussion of another mode, BS to 5 mu mu. So we use 26 data to update the recent to update the branch fraction measurement, and also the differential decay rate as a function of Q square. So from here you can see that the observed decay rate in the low Q square region is significantly below the standard model prediction based on light cone, sun rule, and lattice QCD. The discrepancy is at the level of 3.6 sigma. Actually, this kind of discrepancy in the decay rate is not alone in BS5 mu. It is also observed in other decays such as B to K mu mu, B0 to K star mu mu, and lambda B to lambda 0 mu mu. However, as we know, decay rate suffers significant theoretical uncertainties from hadronic form factor. Therefore, in order to have a better understanding with a better look at something else, angular analysis is a better way to study new physics effects. So we performed the angular analysis of BS25 mu mu. From the angular distributions, we can extract 8 observables. The results are in general consistent with the standard model expectations, including the CP average observable and also the CP asymmetry. So there is no surprise here. The golden channel to study angular analysis to study angular distributions is actually B0 to K star mu mu. From the angular distribution, we can also determine 8 independent CP average observables, the longitudinal fraction FL, forward back with the symmetry FB, and 6 other observables SI. And using FL and SI, we can define some robust variables P prime I, which for which the form factors cancel out leading order. The previous analysis of B0 to K star mu mu used only run-1 data, but some discrepancies with the standard model predictions in the observable P5 prime was already observed at the level of about 3 standard deviations. So this time we include data collected in 16, and the results are shown here. So the tension in P5 prime remains, although the discrepancy is slightly reduced. Here I compare the LCB results shown in black with results from other experiments, including Atlas CMS and B factories. Apparently, LCB has the highest precision. We also do angular analysis of other B decays, such as B plus to K star plus mu mu. So for P5 prime, the same pattern as B0 to K star mu mu is seen here, although the precision is not enough to say anything more. And another observable P0 seems to have also some tension with the standard model prediction at the level of 3.0 sigma. Okay, now we move to lepton flavor universality test, the last topic. So we define the observables RK or RK star. RK is the ratio of the branch fraction of B to K mu mu, and the B to K star is defined in a similar way. As we know, in the standard model, muons and electrons have exactly the same couplings in electroweak interactions. Therefore, RK is expected to be very close to unity. And the uncertainties related to form factors are largely cancelled. In order to address the experimental challenge in the electron reconstruction due to the electron Bremsstrahlung radiation, we use the so-called double ratio technique by introducing the control channel B to JSIK or JSIK star. In the previous analysis, we only used the rank 1 and the 15 and the 16 data. There was a discrepancy in the low Q-square region. Namely, the observed RK was somewhat below unity. The discrepancy is 2.5 sigma. The new results using the full rank 1 and the rank 2 data sample, and this discrepancy still remains, and it increased from 2.5 to 3.1 sigma. On the left, you can see the K mu mu and the KEE distributions for the signal channels on the left and the control channels on the right. On the right plot compares the SCB recent results with the Bell and the Barber experimental results. We also studied the lepton flavor universality in other decays, such as lambda B to PKL, and the measured value is also below unity, although with a sizable uncertainty. In B0 to K star 0 mu mu, the measured K star is still below unity, and the discrepancy is at the level of 2.1 to 2.5 standard deviation. So you can see how this looks like in the low Q-square region. So this kind of a summary. CP violation in Cook sector is measured with higher and higher precision and still broadly consistent with the standard model with the secant picture. On the other hand, there is already hint of leptonic CP violation at neutrino experiments. A few anomalies in B to SL transitions persist, such as hints of lepton flavor universality violation, anomalous angular distributions. And it's interesting to ask whether there is any connection with the anomalies in the newer GMAS2 results. And more results are in the pipeline, and we are coming out in the near future. And as I said, there are many other interesting results not mentioned, such as spectroscopy and production. In the future, exciting opportunities are expected with the upgraded SCB detector, which will accumulate about 50 infrasound band for data, and also LCB phase 2 upgrade, which will accumulate even more, about 300 infrasound band, and also the Atlas and the CMS-B physics programs at the high luminosity LHC. This brings us to the end of my presentation. Thank you.
Okay, thanks. Thanks, Yufeng, for the very nice talk. So we only have time for very quick questions. Well, 2. Okay, so you can go ahead.
I have a question regarding the neutral D mesons. You presented some nice new results that showed D0 mixing, D0 bar mixing. I remember a few years ago, there was a claim by LHCb of having found CP violation in the decay of neutral D mesons. What happened to that? What's the status of that? Is there anything new?
Okay, yeah, you're right that the CP violation D0 to actually, it's the ACP of D0 to K kind of PAPA was observed a few years ago. And we are currently updating this using the full run 2 data sample, and stay tuned. You will soon hear about the new result.
That one other question, when you compare the unitarity triangle status before LHC and now, it seems like now the error on alpha was actually bigger than before.
The error on alpha?
Light blue region has increased, everything else is decreased, but the light blue region seems to have become bigger. How come?
Probably it is, how to say? It is true that we have had huge progress in measuring the angle alpha. But you're right, it shouldn't become worse. Maybe it's just an artificial effect. It is just an artifact.
Okay, thank you.
Okay, so now for the last quick question, Lee, please.
So for B to S, L plus, L minus, will it ever be possible to get inclusive results? And what are, if not, why not?
B to mu plus mu minus?
B to S, L plus, L minus. So you have
B to X, mu minus, you mean? Where X include everything?
Yes.
Okay. Typically, this is the area where B factors dominate. In the hadronic environment, it's difficult for us to do this kind of inclusive measurements. Therefore, we mainly study exclusive decays at LHC.
Okay.
Okay, so because of limited time, so we cannot have more question to ask. You can go ahead offline, is okay? So, Kisu?
Yeah.
Is that okay?
Yeah. For the BS to mu branching ratio, do you have a new combination result of Atlas, CMS, and LHCb?
People are working on it, but it's not out yet.
Not yet.
Yeah. It's in progress.
Progress. Okay. Thank you.
Okay, very good.
Thank
so let us, okay, very good. Let us thank you again for the nice talk. Let us move to the last speaker. Thank you. Last. People, can you share your screen?
Yeah, so let me find that.
Okay.
Okay.
Yeah, we can see your screen, but not your slide.
I can see my screens. Yeah.
Yeah.
Okay. How about now?
Yes, yes, but not in full screen. Yeah.
Okay. Do you see it now?
Yes. Yes.
All right.
Yes.
Okay. You can hear me now, right?
Yes, I can hear you clearly. Okay, so our last speaker is Bipo Boyan. So he will talk about recent results for Bio and Bio 2. Go ahead.
All right. So thank you for inviting to give this minute talk on Bell and Bell 2 on some of the recent results. So I'll be mostly talking about some of the recent results from these two experiments relevant for this particular conference. Just to give you some brief idea about the Bell experiment, because I'll be speaking about some results from Bell. So Bell is the first generation of B-factor experiment along with the Babar. And we operated this machine during 1999 to 2010. And then both this experiment used an asymmetric E plus E minus beam for colliding the electron and positron. For example, in case of Bell, we collided the electron at 8 zeV and the positron at 40.5 zeV. And we mostly operate at absolute burst resonance that corresponds to 10.58 zeV for the production of the beam agent. Now, we stopped operating Bell in about 2010, but still continue to publish important physics results. In fact, last year we published 2 PRL for ZHEP and 15 PRD. Of course, I think in 30 minutes talk, I'll not be able to talk about most of the results which are being published. So I'll be picking up some really important results which are relevant for this particular conference. That's the goal here. Okay. Now, moving from CAG-B to super CAG-B, so we are increasing the luminosity by a factor of 30, and that is being done by increasing the beam current, this is the equation for calculating the luminosity of the beam factor is. So increasing the current by a factor of 1.5 and also decreasing or squeezing the beam at the interaction point by a factor of 20 to get overall increase in luminosity by a factor of 30. So if you look at this particular table on the right, so in case of CAG-B, we had a peak luminosity at 2.1 times 10 to the 34. per centimeter square per second, whereas in case of super CAGD, we're aiming at 6.5 times 10^35 per centimeter square per second. So we started collecting, operating BEL2 around 2019, and we had the last run this year on July 5th, and then we went for the summer shutdown. And then in fact, we have already achieved the world luminosity record of 3.1 times 10^34 per centimeter square per second, 22nd June. And so far, we have collected about 213 meters continuum data at BEL2. So most of the results that I'll be presenting in this particular conference uses data which is about 1/3 of whatever is already on the disk, basically. All right, so you must have seen this detector before. So this is the BEL2 detector, where we have a new vortex detector with 2 layers of silicon pixel detector and 4 layers of silicon double-sided strip detectors for measuring the momentum of low energy particle, and also for measuring the vortex of the particles that have been produced from the first collision. So then around that, so we have a new central dip chamber, which is smaller cell size for measurement of the particle momentum. And then particle identification is being done at the time of propagation counter. This is in the barrel part, and this aerosol-based read detector, which is in the forward part for the particle identification. For the calorimeter, for the electromagnetic calorimeter, we are still using the cesium-weighted crystal from the BEL, whereas the electronics has been replaced with a new set of electronics for faster readout because of the increased luminosity. Of course, the event rate has gone up significantly. Now, the K-long and the muons are detected in this RPC detector, which is in the barrel part is made of RPCs, and in the AND caps, it is mostly made of the scintillator with WLS fiber and WLS 15 fiber, and also PPCs. Now, to talk about some of the physics results of which are making some news right in recent time. So let us start with discussing about the lepton or violating processes that we have been studying in recent time. And in fact, observed neutrino oscillations clearly, at least in the neutral lepton sector, clearly signals violation of the lepton favor. And so we are asking about the same thing in the charged lepton case. Okay, so that is the interesting case of studying the LFV processes in the charged leptons. In the standard model, these processes are extremely suppressed, and there's been after inclusion of the neutrino masses. And that's mostly because the neutrino masses are expected to be much smaller compared to the electron scale. And in fact, if you calculate the branching ratio for process like tau to L gamma in the standard model, so branching ratio comes out to around 10^-50, 10^-54. So these are, of course, experimentally not possible to look for, at least in the standard model. But I think that smallness makes it easier for us to look for this kind of process in models beyond the standard model of particle physics. That because many extensions of this standard model, such as the SUSY, the little Higgs model, and extra dimension predict violation. In fact, in case of tau decays, the branching ratio can be as high as 10^-8 for some of these BSM models. And this 10^-8 is something that is within the reach of BEL2, and that is what we are aiming at once we have the full data set from BEL2 experiment. Now, most of these sources are currently LFV sources, that is for the charged lepton cases, and mostly dominated by the Baba and Bell experiment at this time. And most of these results are coming from tau decays in this most because of the fact that it's a heaviest lepton, so there's less Z suppression compared to the muon. And there's also strong coupling to the new physics contribution. And of course, there are many more possible LFV decays that can be studied using the taus. Now, recently, Bell has come up with this new result on tau to L gamma using the total integral luminosity of 988 inverse lambda 1. And this is the largest number of tau pairs is being recorded by any +7 experiment so far. So for this analysis, we look for, on the signal side, we look for a single lepton and also the number of photons to be equal to 1 on the signal side. Whereas the text side of the tau is being reconstructed from the one-term decay, such as tau decaying to a lepton and neutrino pair, and pi neutrino and also a rho neutrino. So compared to the last analysis was published, so this is an improved, we use improved analysis techniques, including additional variables to improve the signal to noise ratio, and also in blind analysis mechanism adopted for to reduce the experimental bias in this case. Now, to extract the signal yield, we do an unbind maximum likelihood fit to these two particular variable called MBC and also the unit square root of S. And then you can see the plot on the right-hand side for both tau to mu gamma and also tau to e gamma. So here you can of course see the blue, the signal region is being encircled with this magenta line for both the cases, and the blue, the squares are the signals related to events. So the major backgrounds in this case are coming from tau decaying to a lepton and a neutrino pair, and also the ISR or the big background processes, and also coming from the E plus E minus 1 to lepton pair plus ISR and big background processes. So in case of in terms of the observations that we have made here, so we expected a total background of about 6 events for tau to mu gamma and about 5 events for tau to E gamma, whereas we have observed 5 events in both cases, which is consistent with the expected background. So we have set an upper limit at around 10⁻⁸ for both the tau to mu gamma and the tau to E gamma. And for the muon channel, it is the most stringent limit so far. It's been so this is into archive, and of course you can also refer to this particular talk in a parallel session for looking at the details of this particular analysis.
Excuse me, can you speak louder? Because there's some background noise, echoes from audience. Some people.
Okay.
Okay, now
All
much
right.
better. Very
it's
good.
much better. Okay, fine.
Yes. Very
Okay, so then there is another study which is being done to look at B0 decaying to tau and lepton. Again, this can, in principle, can occur by neutrino mixing. The rate is expected to be very small, it's around 10⁻⁴, which is again beyond the reach of any experimental facility. But in some neophysics model, this branching ratio can be as high as 10⁻⁹, and that's the basically goal of this particular analysis. And for to search for this particular decay, we use a full 711 femtobarn of data at epsilon 4 as resonance. So here in this case, we do not do an exclusive reconstruction of the signal side tau because of the fact that it's difficult to reconstruct taus. So we, rather than that, we reconstructed the tag side using the hadronic decays, and we used the initial reconstructed the tag momentum and also the E plus C minus initial momentum to determine the signal side B momentum. And once we know that, because we can measure the lepton energy and also the lepton momentum, we can calculate this missing mass, which is shown here in this particular equation. And of course, for correctly reconstructed events, so this missing mass should peak at the tau mass. So the background for this process mostly comes from B to C kind of transition and also B to E value decays. And then for extracting the signal, we perform an unbind maximum likelihood fit to this MBS distribution, which is shown here on the right-hand side plot for B2 tau mu and also B2 tau E channel. So again, we do not see any significant signal yield for both these cases. So everything is consistent with the background. So in case of tau to mu, so we see this B2D minus 5 plus component here, but again, this is as per the expectation. So in the absence of any significant signal yield, we put an upper limit in the range of 10⁻⁵ for both this both the electron and the muon channel for this particular process. So I think there's a significant amount of improvement that can be done in this particular branching ratio. I think that's something that we'll be looking forward to do in case of BAL2. Okay, so what is the prospect of lepton pair violating studies at BAL2? So BAL2 is going to be collect about 10⁻11 tau lepton pairs compared to 10⁻9 that is presently available with us. So I think we'll be looking, we should be able to do more than whatever we have been doing so far. And of course, the sensitivity is going to depend on the background. For process like tau to 3 leptons, the mode is still going to be very clean in case of BAL2. But for process like tau to mu gamma, so we need to have better understanding and control of the background, to reach the desired sensitivity. So in fact, this plot summarizes what you should be expecting with 15% of BAL2 data in about 10 years time from now. So you should be able to go down all the way to 10⁻⁹ to 10⁻⁻10 branching ratio upper limit for most of the channels that can be studied with BAL2. Now, moving on to another topic, which is of interest in recent times. This is lepton pair universality. I think we heard about that in the previous talk. So in the SUNA model, we expect the gaze coupling to the three-generation leptons to be independent to the flavor. So that's what we call the lepton flavor universality. And in fact, we have been seeing several discrepancies in the B decays recently related to the LFU processes. For example, if you look at the B2D star LU, where we measure this RD and RD star, this is a tree-level process, of course, with a higher branching ratio of about 10 to the power -2. Whereas this RD seems to be consistent with the standard model prediction, but this RD star, the global average is about there is a 3.1 sigma discrepancy with the standard model for the RD star. Now, Bell has recently come up with a new result, which was published in 2020 using semi-electronic tagging. Here, this RD star and RD, so they both agree with the standard model. For example, RD star agrees with the standard model in 1.1 sigma, whereas RD agrees with the standard model within 0.2 sigma. But the global average still, the discrepancy remains. I think that's something that we still need to study in more detail in case of BAL2 and of course at LSCB. For there's another process which is of interest is specifically to look at the B2K star LL. This is again a loop level process. The branching ratio is expected to be very small, but just because the loop level process, we can have new physics in the loop that can change the branching ratio, and also it can introduce LFU processes in this particular study. So here again, similar to the RD and RD star, so we look at mostly RK and RK star, depending on whether it is a K star or a K. Here in this case, you can see this plot for RK star as a function of various Q square bins. And then of course, so this is the standard model prediction, this is at unity, but in the lowest Q square bin, we see some significant deviation between the standard model prediction and the measured using both the B0 and then B plus mode. So of course, this largest deviation is seen in the lowest Q square bin, and this is similar to whatever LSCB has seen. Now, recently, I think we heard about that in this previous talk that they have LSCB has claimed lepton flavor universality violation at 3.1 sigma, which is reported in this particular archive paper, and they have measured this RK plus to be equal to 0.846. So again, this is something that requires more study, and of course, something that BAL2 is going to look at more serious study at some point down the line. Now, the same process, the lepton flavor universality, can be also studied, further studied by exploring other decays like B0 to K star, tau plus, tau minus. That is what is being done in this particular analysis. This is again highly suppressed in the standard model. It's an efficiency process. The expected branching ratio is in the range of 10 to the -7. And of course, this can be important because it's a third generation of the particle, the tau. So there's a new physics that couples strongly to the third generation of particle that can be exploited in this particular decay. Again, the full data sample from the Bell experiment has been used to search for this particular decay process. It is, of course, experimentally is very difficult because of the presence of neutrinos in a final state. That makes a full reconstruction of decay very difficult. So we use this, the B tag that tags that the B is being reconstructed completely from the hadronic decay mode. The tagging efficiency, of course, is 0, but it gives you high purity, pure sample. The tagging efficiency is around 0.24%, whereas the signal side tau is being reconstructed from electronic decays of either an electron or a muon, and also from tau decaying to a pion and a neutrino. The signal selection efficiency is, of course, low. It is around 1.2 times 10 to the -5. And we look for the signal in this case by fitting the extra energy in the ECL, which is the calorimeter, but that is not associated with either the base tag, the tag set reconstruction, also the signal set reconstruction. And we define the signal region to be less than 0.2 ZeP on this particular variable. So you can see here on the right-hand side plot, the energy in the extra energy in the calorimeter, and of course again everything is consistent to it the background, so there's no bump that we have seen. In fact, in terms of the observations, so we have seen -4.9 plus -6.0 for the signal in the lowest background that we expected. So this 90% confidence interval has been put at 2.2 times 10 to the -3 on this particular process, and this is the first experimental limit on this particular decay. So again, there is a significant amount of room that is available to go from 10 to the -3 to 10 to the -7, and of course, this is something that BAL will be looking at. Now, moving on to another topic, which is the dark sector physics. So, of course, we all know about the dark matter, which is for which we have strong astrophysical evidences for the existence of the dark matter particles, but it's all based on gravity. But its nature still remains a mystery. Of course, the most favorable candidate so far is the WIMPs, and we have many underground experiments which are looking for the WIMP. We have not seen any signals so far, and also there's no signal for SUSY at LSC. And of course, so that this implies that we need to go for some new ideas to look for to go away from the standard WIMP paradigm. So that is where the dark sector can come in, and here you can have one or more mediator particle that can couple to this model via various portal. So for example, you can have a vector portal. This is being mediated by a dark photon A prime with a spin 1 and odd parity. You can have a Higgs portal that is being mediated by, again, a dark Higgs, which is a scalar. And neutrino portal, you can also have an action portal, which is with a pseudoscalar A. So you can have a whole particle zoo in this dark sector physics, and that is gaining a lot of interest in terms of the experimental source, even at the B factories. But most of the results which have been published so far are coming from the vector portal, because it's the most viable for the thermal models of the light dark matter candidate. So here you introduce a new symmetry group E1D for the dark sector, assuming that the mediator is a vector boson A prime, which is called the dark photon. And the continuity mixing term, which has been given this particular quantity, is invariant under Gauss transformation of both E1D and E1Y of the standard model. So recently, Bell has come up with the new source on the B0 to A prime, which is going to give you the coupling on the Higgs portal coupling with this standard model, and this has been published recently. Now, if you look at the standard model, so the branching ratio for the 4 lepton channel is very small, it's around 10 to the minus 12, because we look for this particular process by looking at A prime decaying to these various 5 decay modes like 4E, 2E, 2 mu, and 4 mu, 2E, 2 pi, and also 2 mu, 2 pi. This for a reconstruction of A prime. So the 4 lepton channels in this standard model, the branching ratio is expected to be very small, it's about 10 to the minus 12. So that makes it ideal to look for this kind of BSM physics. And of course, we assume that this A prime decays promptly, and also all the dark sector particles coupling to A prime are heavier than A prime. So that means A prime can only decay to the standard model particles. So here in this particular analysis, we look for this A prime in the mass range of 10 MeV to 2.6 eV with 10 to 20 MeV interval. The major backgrounds are coming mostly because of the standard model resonances, which are being misidentified as A prime. Some examples can be Z psi, psi 2s, D0 light measures, for example, the K short rho naught, and also the phi. And you can also have backgrounds coming from E plus E minus going to QQ bar processes, particularly for the 4 lepton channels. And of course, you can have various combinatorial backgrounds with leptons mostly coming from the semiluminary decays of the quarks. So here is a result from this particular source for a B0 going to A prime. So we have not seen any significant signal yield here. So you can see the observed candidate events in this particular plot. Everything seems to be consistent with the background. So in this absence of any significant signal yield, so we put upper limit in the range of 10 to the minus 7 to 10 to the minus 8. But of course, there needs a resonances. So the limit is poorer. It is around in the range of 10 to the minus 5. So you can convert this observation to put constraint on the coupling of the Higgs portal with the standard model as a function of the A prime mass for various dark sector, the Higgs masses, which is shown here in this particular plot. And also you can do the same thing by putting a limit on the coupling as a function of the dark Higgs mass for various masses of the dark photon. Okay, so that's being shown here in this particular plot. Now, there's also recent source to look for E plus E minus going to mu plus, mu minus, and also the Z prime, where Z prime is the dark sector Gauss bosons in the dark sector. And here we look for the Z prime decaying to mu plus, mu minus in this particular L mu minus L tau model, where in this particular model, basically Z prime can couple only to the heavy leptons and the neutrinos, that means muons and then taus. And it can be a solution of the Z-2 problem that we have, the anomaly that we see, but it's almost rejected at this time in the energy range of our interest. So for this particular analysis, we use about 618 inverse pentagon of data from Bell. This is collected at all epsilon and S resonances. And for the signal extraction, so it perform a bin maximum likelihood fit. So we perform about 9,800 fits in total for different Z prime mass in steps of about 1 MeV per C square. So an example of that is shown here in this particular plot. And again, so here in this plot, you can see the significance as a function of the mass of the Z prime. And it's, of course, it's always less than 3 sigma for most of the masses of the Z prime. So you can use this observation to put constraint on the cross section for this particular process as a function of the Z primes, as it's being done here for both born cross section as well as the visible cross section. And you can also put constraint on the Z prime as a function of the Z prime mass, which is the most stringent, at least in this particular mass range that is coming from Bell, which is shown here in red.
Okay, sorry for interrupt. So
yes,
we have only a few minutes to start.
Yeah. So yeah, I'm going to hurry up.
Okay, you can go a little bit quicker to finish. Is that okay?
Okay, fine. So yeah, so then let's move to now to Bell 2 analysis. So this is a radial penguin decays where we look for B2S gamma process, which is again efficiency process. So here, these processes are important because again, you can see that constraint on the 2 Higgs doublet model type 2 from study of B2X as gamma. So that you can see in this plot. So, but for studying case B2K star gamma, it of course there's large uncertainty coming from the form factors. But I think we're mostly interested in looking at the CPS symmetry and also the isospin symmetry, because here, which have been defined this particular equation. So in this ratio calculation, of course, most of the uncertainties cancel. And in fact, Bell has reported around 3.1 sigma discrepancy for in the isospin asymmetry, which was published in 2017. So I think that makes it more interesting to look for this process again in case of Bell 2. So these are the results coming from the Bell 2 with about 615 inverse pentagon data. And of course, you can see at this preliminary stage that everything seems to be consistent with the standard model, and also the PDC value that we have. But I think that's something that we look forward to do again in case of Bell 2 with larger statistics to particularly look at this isospin asymmetry. So another important analysis that is being performed to look for, which is electric penguin decay. So we are looking at a B plus minus going to k nu bar. Again, it's a very theoretically clean process, but it can constrain various BSM models like the leptoquarks, the dark matter particles, etc., etc. So here, most of the analyses are being published on the B2K nu bar. So it's they uses mostly the text that is being constructed either from semi-electronic decays or the hadronic decays with a pretty low efficiency. So in the case of Bell 2, we are using a new approach where we are using an inclusive tag method. That means we're exploiting the topology of the events to look for this particular process using the BDT, where BDT uses the topological features to extract, to separate the signal in the background. And the signal selection efficiency in this case is about 4.3%. So here in this plot, you can see the PT distribution for K plus for various BDT region. So the signal region has been defined for BDT greater than 0.95, whereas we have this control region between 0.90 to 0.95. Now, even though we have not seen any signals event at this time, but this result is pretty competitive at this time because of the increased efficiency, which is about 4.3%. And you can see the importance of this particular results in this global average that is already making an impact.
Sorry to interrupt. Can you finish in 1 minute? Is that okay for you? You're
okay.
already over time for over 6 or 7
Okay,
minutes.
so I'll just highlight this particular analysis coming from Bell 2, and then I think I'll move on to the conclusion. So there's another study to look at B2 theta prime K here. Again, you can see that from Bell 2, again, the results are consistent with the world average at this time. But again, this is something that we'll be looking forward to do with a larger data set. Similarly, for B2 Zesa K long, this is also important for the measurement of phi 1 or the beta angle. Again, the results are consistent with the Bell result with a similar purity, but this is going to be important for the understanding the time dependency violation in this particular process, and also for the measurement of the phi-1 angle. So that's something that we look forward to do. There's also some measurement on the D0 and D plus lifetime. And again, this is also pretty consistent to wall average at this time, but of course it is from the Bell to it is even more precise than the wall average at this time. So it's again shows the importance of the detector, which is the pixel intensity detector, which, that provides a decay time resolution. This is pretty competitive at this time, and it's much better than the previous generation of B factories. All right, so there's also a move to look at B2 D star K pi, and this is for particularly for D and K. So we'll be looking at the measurement of the angle phi-3, which is considered to be a golden mode for the B factories. And we are also looking at this Bell-2 analysis to combine with a Bell measurement of phi-t. So this result, the combined result is going to come soon. And I think that's going to be something that we look forward to do. All right, so this I can skip because of the time, but we hope to have about 15% of our data by 2031. So we are having a long shutdown next year for installing the pixel detector, which is going to be the second innermost layer. And also there will be some PMP replacements going to be done for the top. But then of course, after that, it should be continuing to run and then collect about 15% of one by 2026 and 15% of one by 2031. All right, so this is the conclusion slide. So in the flavor factory, basically, it provides a very rich program in both the tau physics as well as the B physics and also the charm physics. And it provides a masculine environment. It's great for physics studies with the pi-0 and the gamma and the orange neutrino. Inclusive analysis is possible because you have the full control of the event kinematics. Bell continues to produce important physics results which are sensitive to BSM charges. And of course, we continue to do so for a few more years before the Bell-2 takes over. And for Bell-2, from the Bell-2 perspective, we have already collected 200 femtobarn data. And so again, there's some exciting time ahead in flavor physics, at least in the next 10 years from the perspective of Bell-2. All right, so sorry for taking more time, but I think I'm going to stop at this time. So if you have any question, I can take it.
Okay, thanks very much. Because of the time, you guys need to ask a speaker offline this time. Sorry about that. And thanks very much for everyone's patience this time. Let us close this session here. Thanks all the speakers this session. Thanks.
Bye-bye.
Okay, bye-bye. Yeah.
Bye.